Hey guys, welcome to another computer organization video. So today we're going to be looking at, for the first time, a little bit more into memory. We're going to be looking at some parts of the CPU and a little bit into von Neumann and what actually was his proposed model of the CPU. And we're going to also look at the different hierarchy levels of the different levels of a computer using the divide and conquer principle. So to begin, we're going to start with the first level of memory that the CPU usually defaults to. So this is the register. So a register is just a quickly accessible location which is available to the computer's processor. It usually goes to this first. It's only used for a small amount of fast storage. Even though some of these registers have some like specific hardware functions, they may be only read only or write only. This type of register does not hold like programs and stuff like that. They hold different small values. For example, let's say if you're adding some values, it may be holding this register. You might be writing that value into that register for just a period of time. It may be holding it in the MBR register, or it may be using the MAR register to point to a somewhere in memory to point to that location, and that gets fed into the CPU. So, like I said, these registers are normally at the top of the memory hierarchy and they provide the fastest way to access this data. And a CPU has a different set of data storage known as the registers, and they allow the CPU to execute these different types of tasks at a very high speed, and they are located very, very close to the CPU and inside the CPU, if I'm being more correct. So it really depends on the register. Like I said, it can either hold data or it can point to memory locations that hold data. So the second level of memory would be the cache memory, and the cache memory is a very special type of high-speed memory, much more expensive than RAM memory. This is used to speed up and synchronize with the CPU. The CPU is a very, very fast device, and there's sometimes most things cannot keep up with the CPU. RAM, hard disk drives, they cannot keep up with the CPU. And even hard drives, they don't even interact with the CPU. Just kind of an example. But the CPU pretty much works at a very high speed. And cache memory is, although costlier than main memory, than the ROM and RAM, or disk memory, but they're more economical than CPU registers because the registers are more expensive to make. But as well, even though cache is expensive to make, they are not expensive. They're easier, but they are also located close to the CPU where they can increase that rate of return, that speed. So the cache memory is an extremely fast memory type that acts as a buffer between the RAM and the CPU. So at the second level, although it's smaller in the hierarchy level than the register, it's higher on the hierarchy level than RAM. And this is used to reduce the average access time from main memory. This allows cache memory. It can hold some information closer to the CPU that the CPU doesn't have to travel as fast to the cache memory than the RAM. So it decreases that access time. And the thing about cache, it holds frequently requested data. It holds data that's constantly asked for. So that way the CPU can go to the cache real quick, much faster than it has to go farther for the RAM. So let's say you're walking 10 feet compared to 500 feet. You walk to that 10 feet and come back, you're definitely going to get there faster. You're going to come back to your access point, your starting point, than if you have to walk to 500 feet and back. And even if it's hard disk memory, you're talking about like 2,000 feet. the amount of time it takes to reach these memories is a lot longer than the cache memory compared to RAM, and RAM compared to hard disk drive. So this is when we move into main memory. Main memory usually includes the ROM and RAM, which is located pretty close to the CPU, and this enables the CPU to access this data quickly. So what is ROM? ROM pretty much stands for read-only memory, and this is data that cannot be modified after the manufacture of this device. It's pretty much non-volatile memory that permanently stores instructions for your computer. So what kind of instructions does it store? It can store maybe the BIOS setup of your computer. It can store the startup of your computer. It can also hold something like firmware. So what is RAM? So RAM is volatile memory that temporarily stores the files that you are working on. Say you were playing a game or you are on a web browser. So that memory where you are pretty much constantly changing, constantly modifying, that is being stored on your RAM. So that's why when you have 20 tabs open on a browser and your computer starts to slow down, it's because you are adding more and more memory to your RAM and slowing the capabilities of your computer. So main memory, like I said, is where these programs and data are kept when the processor is actively using them. Say you have a file, an essay, that is not currently open. It's somewhere stored in your computer. It is actually on your hard drive or your SSD, or even if you have it on a USB or something. It is not being currently used by the computer. So what happens when you actually open that word document? What's going to happen is there's going to be it's going to be opened on your RAM, and you are going to be able to change it on your RAM. And once you save that and close that, that copy is now going to be saved onto your hard drive or your SSD or anything that you're doing for your secondary memory. So, like I said, when these programs and data become active, they're copied from secondary memory. That secondary memory is your hard drive or your SSD, and into main memory. It's going to be RAM, because remember, ROM is read-only memory. You can't write anything. So this is where the processor can interact with them. Let me see. And my laser pointer. So what is secondary memory? So secondary memory pretty much refers to storage devices such as hard drives or SSDs. All right, and this also refers to removable storage media, such as you inserting a flash drive or CD or DVD. This refers to external types of memory devices. And unlike primary memory, secondary memory is not accessed directly by the CPU. What needs to happen, it needs to be copied into primary storage. Like I said, if you are writing an essay and you're accessing it from your computer, for you to change it, it needs to be copied into RAM, and that's where you can change it, and that's where the computer, the CPU, can actually interact with that essay. So, secondary memory, hard drives, this is where the programs and data are kept on a long-term basis. If you turn off your computer, you are not going to lose your files. But what if you don't save that essay? What if you are working on it and your computer suddenly dies or something like that? When you turn on your computer, your files, for the most part, if there's no recovery method that was able to go through, your files are completely gone because it was on RAM. It was on random access memory. That means you were not saving it onto the hard drive, which is the permanent. It's the permanent storage. So, like I said, what we went through is the basic levels of memory. We have our registers. We have our cache as a secondary. We have our third level, which is our main and primary memory, includes the ROM and RAM. And our secondary memory, that can be hard drives, SSDs, USBs, external hard drives, or DVDs. And there's much more, promise you that. So this is when we are going to start talking about the hierarchy level of computer. So think about a computer. Think about how complex a computer is and how much you need to know about how to make a computer. It can be very, very difficult. So the way we can try to peel open and understand the computer is we need to divide it into modules. We need to design each module separately to perform a specific task. And we need to make these modules, we need to create them in a way so that they can interface with other modules. So, what I'm trying to say is that this machine is built on a hierarchy of levels, and each of these levels have their own function, and they have their own particular set of instructions that they need to call upon to carry out whatever task they need. So this is a computer level of hierarchy. We have 7 levels from 0 to 6. The top one is the user level, is which we know the most. So each virtual machine layer is pretty much an abstraction of the level before it. The machines at each level execute their own instructions. Each of these levels execute their own instructions. And they call upon the machines at lower levels to perform the task. And these computer circuits are pretty much what carry out the work. These digital logic circuits carry out the work. Notice it's at level 0. That what's pretty much creates our computer. So we're going to start off with the highest level. It's called the user level, and this is where the program execution and user interface level works. For example, what I am doing right now, I am on PowerPoint. This is the user level. This is where I can execute my programs. This is where I can do whatever HP wanted me to do an ease of access, And this is the level we are familiar with. You're very familiar with. So at this level, we run programs such as word processors, graphics, and games. And usually the lower levels are nearly invisible to us. We cannot see what's happening behind the screen. So this is level 5. And level 5 usually deals with the level that we write program languages in, such as C, Pascal, Lisp, or Java. The reason we call these high level languages is because the computer we cannot write a C program and the computer knows exactly what we're saying. These need to be broken down into assembly language and into machine language so the computer now finally understands what we're trying to say. Remember, a computer speaks in zeros and ones, they speak in binary. But when we're doing high level language, are we writing in zeros and ones? No, we're not writing in zeros and ones. We need some way to break that program down into binary language. So what we use is we either use a compiler or an interpreter. So these compiled languages such as C are translated into assembly language and then assembled into machine code. So the 4th level is the assembly language level. This is where we're focused on assembly code. So this acts upon the assembly language produced from level 5, what we produce from breaking down our high level language. So these compiled higher level languages are translated into assembly, which are then assembled into machine language. So the 3rd level is very, very, very important. So, all of these levels are very important, but this is where we focus on our operating system. So the system software level deals with the operating system, and this is responsible for multi-programming, protecting our memory and system resources, synchronizing our processes, and a whole bunch of important functions. And the assembly language that we had before in our previous levels usually pass by here without any modification. Our second level is the machine level, known also as the instruction set architecture level, or ISA for short. And this consists of instructions that are particularly to the architecture of the machine. They are a little bit too advanced for us to know. We probably will know about them later when I do computer architecture course, that when I create this course after computer organization. And these programs are written in machine language, so there's no need for compilers, interpreters or assemblers, because if it's created in machine language, the computer can understand it. And there's no reason for us to have compilers or interpreters or assemblers. And level one, this is the control level, and this is where our control unit decodes and executes the instructions and moves data throughout the system. The control unit is an integral part into the CPU, and we will see it in just a couple slides. We'll just have a brief overview of the control unit. So what the control unit does, it just makes sure that the instructions are decoded and executed properly. If we have some interrupts in our fetch and decode cycle, then there's going to be some problems with the computer, that it's not properly working or it's not executing the right instructions, and there's going to be an interrupt cycle where this control unit needs to figure out the proper way to execute these instructions. And the last level, and the most basic and fundamental level, is the digital logic level. And this is pretty much the level where we find our hardware. This is where we find our digital circuits, and they consist of gates and wires. And these components, these gates and wires, they implement the mathematical logic of all the other levels. This is where we find our circuits, gates, wires, and our logic. So this is where we will transition a little bit into the CPU. So the ALU, which is located in the CPU, is the arithmetic logic unit, and it's a digital circuit, and it's used to perform arithmetic and logical operations. And it's very, very, very important into the CPU. And most of the operations of the CPU are performed by these ALUs. You can have multiple ALUs, but for simplicity's sake, we will only focus on one. And it performs addition, subtraction, division, and multiplication. But most ALUs, you will find addition and subtraction, just because division and multiplication, implementing that into an ALU is more expensive. And continuing with the ALU, so this is the part of the CPU that handles all the calculations that the CPU may need. Just like we said, addition, subtraction, multiplication, or division. And they deal with mostly logical operations such as AND, OR, NOT, XOR, NOR, and NAND gates. And we will know exactly what AND, OR, NOT, XOR, NOR, and NAND. If you have never seen it before, we will know exactly. We will have extensive practice with these logical operations in the future. We are just touching base on these right now. There's also bit shifting operations, and this pertains to moving the positions of bits a certain number of places to the right or left, depending if we want to do like a multiplication operation or division operation. So then we have arithmetic operations, and this just pretty much refers to bit addition and subtractions. Although, sometimes multiplication and division are used. But before we ever go into bit shifting or arithmetic operations with bit addition or subtractions, we will be looking at how to find binary and how to change it into octal and hexadecimal, or even from octal to hexadecimal to bit. There's a lot we need to know before we can actually get to there. So, like I said, we are looking at the control unit. This is just a super brief look at it. We will go more into depth when we have the CPU chapter. So the control unit pretty much regulates and integrates the operations of a computer. So it pretty much referred as the central nervous system because it selects and it interprets the instructions of the CPU and coordinates the execution. It controls the instructions. It controls what's happening throughout these steps. And the control unit is so important into the CPU. This is just a brief overlook. Like I said, we will go more into depth during the CPU chapter for this course. So, what are the jobs of the control unit? So, the control unit obtains this data and instructions from memory. It interprets it and decodes the instructions into commands and signals, and it controls the transfers of instructions and data in the CPU. So that's why it's called the central nervous systems. It's the pretty much the most integral part into the control unit alongside the ALU. So it just pretty much coordinates the parts of the CPU. So before we finish this video, I'm just going to touch base on the von Neumann model. So in 1945, John von Neumann, he just pretty much wrote a report on the first drafts of a report of EDVEC. In this report, he detailed the basic structure proposed and became known as the von Neumann machine. So what he said for the computer, the basic structure of a computer, is that it needed to contain memory, which contains instructions and data, a processing unit for performing arithmetic and logical operations, and what is that? That's the ALU, and a control unit that interprets instructions. So today's stored program machine architecture, there's three hardware systems. We have the CPU with a control unit, an ALU, and registers for that small storage areas that we spoke at the beginning. We have a main memory system, and that holds the programs that controls the computer operation, and some sort of input and output input output system, something that we can input and get an output. That's what pretty much constitutes a computer: a CPU, a main memory system, input output system. We need to have a control unit in that CPU and some sort of arithmetic and logic calculator, if you want to say it that way. So the thing about the von Neumann model, it's one bad thing about the von Neumann model. There is only a single data path between the CPU and main memory, and it's known as the von Neumann bottleneck. So you see that there is only one path. The problem with that one path, it can only go one way back. You do not have multiple ways to get into main memory. So what does that do? It slows down the computer, or if there's an interrupt in the computer, there's a chug in the computer, like it's going to be stuck. Like I said, this is just a basic structure proposed in 1945. So this is a very rudimentary type of structure, but it pretty much based off what we built upon. So what we have is we have our registers here in the CPU. This is where we have the program counter. We have our other registers like the MAR, MBR, stuff like that we will learn much later in this course, but right now we do not need to know them right now. Just this is where our registers are located. This is where we can hold our data. As you can see, it's in the CPU, super close to the CPU. CPU can just grab it in there. That's why it's level 1. It's so close. Then we have our ALU. So what happens? let's say we write some data into one of these registers. It can be calculated. It can have some sort of arithmetic in here. We can move it in here, and we can store it back in the register in here. And what does a control unit does? It pretty much interprets the instructions. Let's say it needs to go into memory. It interprets the instructions, goes to memory, finds whatever memory we need, brings it here, goes into arithmetic logic unit, calculates whatever it needs, stores it in registers. So as you can see, this picture is pretty basic of what a CPU does. But you can see how many things can happen. It can grab stuff from memory, go into the control unit, which interprets instructions, tells it where to go. ALU can perform some arithmetic or some division or multiplication, whatever you want to say. And we haven't even talked about the input and output systems yet. So this can get very, very messy very, very quickly. And that's why the computer is just such a hard piece of hardware to understand, because there's so much happening so fast. So, and just to finish out the video, this is just a general depiction of the von Neumann system. And pretty much the control unit helps employ the fetch, decode, execute cycle to run programs, to run whatever you need. And we will be talking about the fetch, decode, execute cycle in the next video for sure. And this is the end of the second video. I hope you guys took notes. We will be learning, like I said, about the fetch, execute, decode cycle. It's a little bit difficult, but we need to learn it, and it's very important to understanding the CPU and the processes and the control unit. And this is everything programming, guys. Please leave a like, comment, and subscribe. I will see you guys in the next video.